You write a piece of code, it passes every unit test, it executes exactly as written, but the moment you deploy it to a production environment, it completely fractures under the invisible pressures of the system architecture. Take a standard rate limiter. Generative AI will write this for you perfectly. It uses the classic token bucket algorithm, written cleanly in Go. You configure it to allow exactly 100 requests per second for a given user. But when you check the live telemetry, there is a massive gap between intent and reality. On the left, the configuration states a limit of 100 requests per second. On the right, the actual throughput for a single user is sitting constantly at 500 requests per second. You are not under a sophisticated attack, and the local logic is flawless. On each individual server instance, no API key is exceeding 100 requests per second. The problem exists entirely in the deployment topology. You are running 5 separate server pods behind a load balancer. When a user sends a surge of traffic, the load balancer distributes those incoming requests evenly across all 5 pods. Each pod sees 1/5 of the total traffic, and each pod maintains its own isolated rate limiter in local memory. Since every pod allows 100 requests per second and you have 5 pods, the effective rate limit across the network multiplies. 5 times 100 equals a total allowed throughput of 500 requests per second. AI assistants introduce this exact vulnerability into production systems constantly. AI evaluates code assuming a single process execution environment. It lacks the spatial awareness to recognize how a load balancer distributes traffic across a physical network. You cannot enforce a global constraint using local state. Every individual piece of code in this setup is behaving correctly, but the system as a whole is entirely wrong. The first instinct most engineers have is to manipulate the routing layer. Using sticky sessions, you can force the load balancer to route all requests from a specific user to the exact same pod, forcing all of their traffic through a single memory bucket. But mapping traffic with sticky sessions exposes an immediate load distribution failure. If one heavy user generates 80% of your API traffic, all of those requests are pinned to a single node. That specific pod overheats, while the other 4 sit completely idle. You cannot autoscale out of this bottleneck. Even worse, when that overloaded pod inevitably restarts, its local memory is wiped. The user's rate limit history vanishes. They start with a completely fresh token bucket, instantly granting them a massive burst of free requests every time a node cycles. The second instinct is to hack the local math. If you want a global limit of 100 requests per second across 5 pods, you configure each individual pod to allow exactly 20 requests per second. This strict division relies on the false assumption that load balancers distribute traffic with perfect mathematical symmetry. In reality, routing is messy. If one pod receives 40% of a user's traffic due to natural variance, its strict limit of 20 will reject legitimate requests, even while the other 4 pods have plenty of unused capacity. The math also disintegrates the moment your infrastructure scales. If a traffic spike causes your cluster to autoscale from 5 pods to 10, your global limit instantly doubles to 200, unless you dynamically reconfigure the hard-coded limit on every individual pod mid-surge. Manipulating load balancer rules and fracturing local limits are fragile workarounds. They attempt to mask the true deficit of the architecture. The individual servers have no awareness of what the rest of the cluster is doing. This exposes a rigid law of distributed architecture. Anytime you need a system-wide invariant, like a total rate limit across all nodes, you require shared state. To fix the architecture, we remove the rate limiter from local memory and implement a centralized data store. By connecting all 5 pods to a single Redis instance, Redis acts as the sole source of truth for how many requests a specific API key has consumed. With the data centralized, the next decision is the algorithm. The simplest approach available in Redis is the fixed window counter. A fixed window counter creates a database key for a specific chronological block of time, like the current second. Every incoming request increments a numerical tally on that key. If the tally exceeds the limit within that exact second, the request is rejected. Look at the boundary between these 2 1-second blocks. A user can send 100 requests in the final milliseconds of the first second and another 100 requests in the first milliseconds of the next second. Both windows technically respect the limit, but the user just pushed a massive spike of 200 requests through the API almost instantaneously.
To eliminate that boundary burst, you need an algorithm that continuously moves forward. The sliding window log solves this by discarding fixed blocks and instead tracking the precise timestamp of every individual request. Using Redis sorted sets, each request adds a new timestamped entry. Before evaluating a new request, the system drops any timestamps older than 1 second and counts what remains. The window slides forward precisely with the clock. But perfect accuracy carries a heavy infrastructure cost. If an API key is allowed 10,000 requests per minute, you are storing 10,000 individual timestamp entries per user, continuously. At high traffic volumes, this causes unbounded memory growth in your Redis cluster. You also have to account for the performance penalty of abandoning local memory. Checking Redis requires a network hop. To prevent race conditions and keep latency low, the logic must execute atomically on the server side, using a Redis Lua script, rather than passing data back and forth to the application pod. A pure fixed window is too sloppy to prevent burst abuse, while a pure sliding log is too memory-intensive for high-throughput APIs. You need an algorithm that splits the difference. The optimal solution for production rate limiting is the hybrid sliding window counter. This algorithm uses just 2 simple fixed window counters. In this diagram, the previous window recorded exactly 80 requests, and the current window sits at 30 requests. Instead of logging thousands of exact timestamps, it continuously estimates the rolling limit using a weighted interpolation formula. If the time cursor is exactly 30% into the current window, it means 70% of the previous window still overlaps with our 1-second lookback. We take 70% of the 80 requests from the previous window and add them to the 30 requests in the current window. The calculation yields an estimated total of 86 requests over the past rolling second. Because 86 is safely below the maximum threshold of 100, the incoming request passes through. Regardless of whether a user sends 100 requests or 10,000 requests, this calculation only ever requires storing 2 integers in Redis. The memory footprint remains completely constant. The hybrid counter achieves the smooth, boundary-free accuracy of a sliding window while maintaining the extremely high-performance memory profile of a basic fixed counter. With the math solved, the implementation becomes a system-wide architectural decision dictated by your latency budgets and accuracy constraints. Centralized state comes with a mandatory toll. Adding a 1 millisecond network round trip to Redis is negligible for a standard web request, but it severely degrades the performance of an ultra-fast sub-5 millisecond API. If you cannot afford the network hop, you can move the rate limit enforcement completely out of the application code. Deploying an API gateway in front of the load balancer creates a single architectural choke point that enforces limits before traffic ever hits the individual pods. For latency-sensitive systems that still require application-level logic, you can implement a local with sync model. Pods enforce strict limits in local memory, but periodically reconcile their counts with a central data store to ensure they stay relatively close to the global limit. This creates a clear decision matrix. If you need exact, strict limits for billing enforcement, you must accept the latency cost and use shared Redis. If your system requires absolute minimal latency, you trade a small amount of accuracy by routing enforcement to a gateway or using a local sync. But relying on centralized infrastructure forces you to answer a final critical question about failure modes. What happens to your API traffic if the Redis cluster suddenly goes offline? For the vast majority of services, the correct choice is to fail open. Rate limiting protects the system from abuse, but taking your entire service offline to enforce a limit causes more damage than temporarily allowing too much traffic. A well-designed system prioritizes forward momentum. When a component fails, the architecture gracefully degrades, absorbing sudden shock while continuing to push core traffic steadily forward. Looking at the telemetry now, the gap between intent and reality is closed. With a centralized data store managing the state, the configuration of 100 requests per second translates to exactly 100 requests per second passing through, regardless of how many pods are active in the cluster. The most dangerous flaws in distributed engineering are rarely bugs in the code itself. They are flaws in assumptions. They occur when you fail to align perfectly valid local logic with the physical realities of the deployment topology.